Hello pre-calculus students. In this video we will discuss exponential growth, and this is a special case of exponential functions. Okay? So exponential growth is defined in terms of the end behavior, that the limit of f of x as x approaches infinity is infinity. In other words, as x gets bigger and bigger, f of x keeps getting bigger and bigger, and it grows forever without bound. And then the limit of f of x as x approaches negative infinity is 0. In other words, as x goes towards the left or towards negative infinity, the function will get closer and closer to 0. So one of the examples of this is the function f of x equals 2 to the x. Okay. So I can actually mark my graph here based on this function. So when x is 1, f of x is 2. When x is 0, f of x is 1. When x is 2, f of x is 4. And I can then draw in a pretty decent looking graph of this function. And you can see here that as x increases, we're just doubling up, we're just multiplying by 2 again and again and again and again. So in other words, as x goes towards positive infinity, as we go towards the right here, f of x goes towards positive infinity. As x goes towards negative infinity, in other words to the left, f of x will approach 0, getting closer and closer to the x-axis. So this is an example of exponential growth. Okay? Now another way that we can write this function, which you will sometimes see, is f of x equals 1/2 to the negative x. So in this case, you don't have a whole number here, or a number greater than 0 here for your base. You have 1/2, but it's raised to the negative x. And I'm going to show you why these two functions really are the exact same thing. So this is really saying 1/2 to the negative 1 to the x. Okay. So in other words, what I'm trying to do here is to make this exponent positive, or the variable positive, and take it one more step further. 1/2 to the negative first power, that's just taking the reciprocal, so that's 2 to the x. So in other words, I can say that 1/2 to the negative x is the same thing as 2 to the x. So this tells me that for a function that has exponential growth, I can either have a base that's greater than 1 and a positive variable, or I can have a base that's less than 1 but greater than 0, and an exponent that's negative, and they will produce the exact same result. So this is an example and a description of a function with exponential growth. Okay. Let's go on now and see what happens when we look at exponential decay. Okay. So similar to exponential growth, exponential decay is also defined in terms of limits. And for an exponential decay function, the limit of f of x as x approaches infinity actually goes towards 0, hence the decaying factor. As x gets bigger, f of x gets smaller and smaller and smaller until it approaches 0. As x approaches negative infinity, in other words, x goes towards the left, f of x grows towards positive infinity. So we'll look at an example of this would be the function f of x equals 1/2 to the x. And just a quick thought here is that we can see that this is decay because as x gets bigger, we're just multiplying 1/2 again, and again. So you start out with something, some initial amount, and then you get half of that, and then you get half of that, and then you get half of that. So you get smaller and smaller. Okay. And for this, let's actually make a little table here to help us graph a little bit better. So we'll have x, and we'll have f of x, and we'll have these values. 1, we'll go increasing by 1, 2, 3, 4. Okay. So when x is 1, f of x is 1/2. When x is 2, or 1/2 squared, that gives me 1/4. When x is 3, 1/2 to the third, that gives me 1/8. 1/2 to the fourth is 1/16. Okay, so this is a function that's going to get smaller and smaller as x increases. So if I were to graph this, if I make this x-axis 1, 2, 3, and I'll go 4 increments. This is 1. This is 2. Okay. So 1, 1/2. That's right here. 2, 1/4. That's right here. 3, 1/8. 4, 1/16. Okay. Oh, and I should really add one more point to this. We'll add another section down here. And the point that I should add into this is 0. What happens when x is 0? Well, 1/2 to the 0th power is just 1. So that's my x-intercept. And I'll go one more. What happens when you have -2? So this is 1/2 to the -2, which is 1/2 to the -1st squared. And this is 1/2 to the first power. So 1/2 to the -1st is really just the same thing as 2 squared, which is 4. So 4 goes in here. So at -2, I actually get 4, which is like way off the graph up here. Okay, so to graph this, just draw a line, or a curve, I should say, through all of these points, and there you have it, a graph of f of x to the 1/2, and this is an example of exponential decay, because as x increases, f of x, the y values, get smaller and smaller until it approaches 0. As x decreases or goes towards -infinity, f of x actually grows and gets larger and larger. Now there's another way that I could write this function. Notice that I have a fraction raised to the positive exponent. This function here, we'll call this g of x so that we don't confuse ourselves. So we'll call this g of x is equal to 2 to the -x. And these functions are actually identical. They actually produce the same results, and I'll show you why. 2 to the -x is really 2 to the -1st to the x. But 2 to the -1st is just taking the exponent of the reciprocal. So the reciprocal of 2 is 1/2. So this function, g of x, and this function, f of x, really is the same function. So for an exponential decay, I could have a fraction with a positive exponent multiplying again and again, or I could have a whole number with a negative x in the exponent, because that's the same thing as having a fraction with a positive exponent. So there you have it, an example and a definition of exponential decay. So going forward, you should be able to look at a graph, look at a function, and determine if it is exponential decay or exponential growth.